Assalamualaikum and good morning. My name is Amir Danish bin Karya Anwar, HC25010. And today we are going to talk about a subtopic in chapter 4, which is thermocouples. So what is a thermocouple? A thermocouple is an active thermoelectric transducer used to measure temperature. It works thanks to the Seebeck effect. It says a voltage generated in a circuit containing two different metals by keeping the junctions between them at different temperatures. So how do you build the thermocouple? It is incredibly simple. It consists of two wires made from dissimilar metals, which are two different metals such as iron and copper, which are also joined together at one end. There are two junctions for the thermocouple. One is hot junction for measuring the voltage, and another one is the cold junction, which is a reference junction. So the hot junction is where the end of the two metals are joined and exposed to the process whose temperature you want to measure. As for the cold junction, it is the open end of the wires that connects to the measuring instrument, like a voltmeter. It is kept at a known reference temperature. On the right side, we can see the diagram of the thermocouple, which has the hot junction and cold junction, and it is connected to a voltmeter. And below is the picture in real life of a thermocouple. Now I'm going to talk about the principle of operation, which is the Seebeck effect. Thermocouples operate entirely on the Seebeck effect discovered by Thomas Johann Seebeck in 1821. So the rule is when two dissimilar metals are joined to form a continuous circuit and the two junctions are kept at different temperatures, a continuous electric current flows. So the output can be produced because we leave the cold junction open to attach a voltmeter. We measure this as a voltage. The magnitude of this microvolt or millivolt signal is directly proportional to the temperature difference, which is delta T, between the hot and cold junctions. The equation concept is voltage is directly proportional to the difference of temperature from the hot junction and the cold junction. You can also see in the diagram which shows the reference junctions inside a ice bath and a copper wire being used, and also constantan and iron. Next is the part 2, when the loop is broken and the voltage is measured. The measured voltage is directly related to the temperature difference between the two junctions. So this phenomenon where a voltage is produced because of the heating of the junction of two metallic conductors is called thermoelectric effect or Seebeck effect. The junction where heat is applied is called the hot or measurement junction. The other junction is called the cold junction or reference junction. And the voltage developed is called thermo EMF. So to calculate the thermal EMF, we can find using the equation below. The temperature is usually expressed as a polynomial function of the measured voltage. Sometimes it is possible to get a decent linear approximation of a limited temperature range. So the equation is E equals to C, and the difference between temperature 1 and temperature 2, T1 is hot junction and T2 is cold junction, and plus K multiplied by the T1 squared minus T2 squared. So C and K are constants of the thermocouple materials, and T1 and T2, as I said just now, is hot and cold respectively. So now it's about the cold junction composition, CJC. To know the exact temperature at the hot junction, the instrument must know the exact temperature at the cold junction. Historically, the reference junction was literally submerged in an ice bath, 0 degrees Celsius, to provide a stable mathematical baseline. Today, modern instrumentation uses cold junction composition, CJC. A separate internal sensor like a thermistor measures the temperature at the connection terminals, and an internal microprocessor automatically calculates and offsets the baseline voltage. So there are multiple types of thermocouples, and the metals are paired strategically to cover different temperature ranges and environments. They are designated by letters. For example, type K, which is chromal or alumal, the most common general purpose thermocouple. It has a wide temperature range between negative 200 degrees Celsius to 1260 degrees Celsius. It is very durable and relatively inexpensive. Another one is type J, which is iron and constantan, highly sensitive and good for low temperature ranges, but the iron lag can rust in oxidizing wet atmospheres. Next is type T, copper or constantan, extremely stable and accurate at sub-zero and cryogenic temperatures, which is below zero. Type SRB, which is platinum and rhodium, high temperature, highly accurate, but it is very expensive. Used in glass and metal foundries. And last but not least is the advantages and disadvantages of thermocoupling. So for the advantages, we can say that it is a active transducer, self-powered, which is no external excitation voltage is required. Besides that, it is also rugged and simple, practically indestructible. It can withstand intense vibrations and extreme environments. For example, in a hot desert which can reach up to 40 plus degrees Celsius, and even the temperature in volcanic eruptions. Next is the fast response. The junction can be made extremely small. It's basically just the tip of the wire, allowing it to react to temperature changes in milliseconds. Next, it is unfortunately low voltage output. The output is in millivolts, so you cannot read high voltages. It is highly susceptible to electrical noise and requires sensitive amplifiers. So it's technically not a perfect sensor to read temperatures. And next is the non-linearity. The voltage does not scale perfectly in a straight line with temperature. Instruments must use complex polynomial math, which by looking up temp tables to linearize the reading, which is going to be a hassle to calculate and measure the temperature. Besides that, it is also lower in accuracy. The thermocouples are generally less accurate and have lower stability over time. So that's why in this modern age, we use more complicated and complex thermostats instead of thermocouples, as it has quite some setbacks that will interrupt the calculation and measurements of temperatures. So that is all from me. Thank you.